Hey guys, how you doing? It's Coach Scott. Let's go ahead and go to our next section. This is Unit 2B. We're going to explore the Bohr model just a little bit more. So, let's see. A scientist named Niels Bohr. So he interpreted these observations, okay, about how the what he was seeing with the hydrogen molecule or the hydrogen atom, and he created a new model of the atom that explained the existence of emission spectra and provided a framework for where the electrons can exist around the nucleus. So, Bohr knew that the wavelength seen in the light of hydrogen consisted of lines in irregular patterns. Now, patterns makes us think something, math, how things work, right? Now, each of these series of lines were named for the scientists who created the model for it. All right. So, in the ultraviolet series, you had the Lyman series. Now, these waves were around 100 nanometers, right? The wavelength. Now, the visible spectra is between 100 nanometers and 1,000 nanometers. This is what we call the Balmer series. And again, this is in the visible spectra and also in the ultraviolet spectra. Now, from about 1,000 to 10,000 nanometers, this is what we call the Passion series. And this is the infrared spectra. We can't see this with our eyes. Okay. So, each of these scientists created a formula using calculus which predicted a series of colors that were emitted. Now, the colors were defined by their wavelength, which we're calling lambda. That's the Greek symbol for lambda, right? Now, these models use the variable n, but no one knew what the n represented. Okay, it was just how the math worked out. So the Lyman series uses the reciprocal of lambda equals r times 1 over 1 squared minus 1 over n squared, and so on and so forth and so on. N being 2, 3 normal integer. Now the Passion series, or the Balmer series rather, they used the reciprocal of lambda equaled r with 1 over 2 squared minus 1 over n squared, with n being 2 plus 1 integers, right? So it started with 2, 3, 4, 5, so on and so forth. Now the Passion series used the lambda reciprocal, 1 over lambda, equals r, a constant, times 1 over 3 cubed, or 3 squared, minus 1 over n squared, n being a integer greater than 3. Okay? Don't worry about the math. It's just these guys did the math and figured out where these colors, these wavelengths were. So this is what Niels Bohr did. Niels Bohr, okay, he said that the n, okay, defined a permitted electron orbit around the nucleus. And what his model predicted, or what he predicted, was that these electrons could orbit the nucleus about like a planet around the sun, right? But only at these permitted radii. So the radii would increase in proportion to n squared, right? So the orbits get much larger as n increases. Now, it had a good point there. Why can't we see the nucleus? Well, it's too small if we were to see it in scale model, right? It would be, I don't know, a piece of pencil lead right there in the center. So Bohr proposed this. He proposed that these electrons would not radiate energy while traveling in the permitted orbit. Now, this violated what we knew about electromagnetism and electromagnetic waves. since orbiting charges should radiate energy. But Bohr proposed that somehow those rules would not apply to electrons in these orbits 1, 2, 3, and 4, 5, 6, infinity. Right? He proposed that the electrons would radiate or absorb energy when they moved between the permitted orbitals. So each of these orbitals represents a different energy level. So the energy the light emitted or absorbed is equal to the difference in the starting and the ending energy of the electron. Okay, so if the electron started at n equal 1 and it was to jump to n equal 2, then it would be 1 over 2 squared minus 1 over n squared, so on and so forth. And that would be the ground state, or the where the electron went when it was promoted to another different energy levels. So what are these energy levels? Okay, for each n, or each energy level, there's an energy level that we designate E sub n. Okay, so the ground state of an atom, is its lowest energy level, n equals 1. So we can call that energy level E sub 1. E sub 2 would be the energy when n equal 2, and so on and so on and so forth. Okay, and again, we're getting into this, we're building our knowledge. So let's take a little quiz break, if you would. Given that Q, capital Q, and Q are the charges of the nucleus and the electron, the positive and negative charges, when they are near each other, their potential energy would be what? Take a break and we'll talk about it. Well, if you had 1 and minus 1, that's 0, right? So you have 0 divided by r, or the radii, or the distance between the charges, times a constant. So you got 0 divided by r, so that would be a negative number. Okay. When an electron is infinitely far from the nucleus, the potential energy of the atom, okay, so Q, all right, has got a minus 1 charge. The nucleus has a positive 1. Look at R. As R gets bigger, it's going to be a bigger number. So when it gets to like 10, that's a 0 divided by 100. All right, it wouldn't be 0. It would be 1 times negative 1. It would be 1 over 100. Okay? So that's going to be a 0 type number. Okay? So as it gets further away, the energy gets close to 0. There's less energy holding it together, or less force. So, permitted orbits for the electrons are given where Rn equal R sub 1 n squared. All right. Which of the below is then correct for the given orbital? Okay. E sub n equal K, well, capital Q times Q over n squared. Or E sub n equal K times capital Q times Q over R sub 1 n squared. Or E sub n equal E over 1 over n squared. Well, if I have capital Q over R, and I sub that in, that is E sub 1, right? So it would be B and C. Don't sweat this, we'll get to it. Okay, so that would be B and C. So since the nucleus, okay, and its electrons have opposite charges, the potential energy between them is always negative. So when R is very, very, very large, the potential energy is 0. Now R is proportional to n squared. So energies will be proportional to 1 over the 1, that's the reciprocal of n squared. Okay? So, let's play. The ground state of hydrogen, N sub 1, is minus 13.6 electron volts. What is the energy when N equal 2? When N equal 2. So take a break and see if you can figure that out. Well, let's see what the answer is. The answer, okay, is minus 3.4 electron volts. Well, let's see how we got that. So E sub n, all right, in this case, all right, would be E sub 2, or the energy. So E sub 1, which was minus 13.6 volts. Get my pen out. See if we got, no, it's not writing yet. I'm going to pause. So, how would I solve this problem? Well, my formula is E sub n, and it's looking for the ground state, okay, or the energy of hydrogen when it's N sub 2. So we're looking for that energy. So if I know what E sub 1 is, which is minus 13.6 electron volts, then in the N, okay, or the energy value of the N sub 2 would be N squared. N is 2, so it would be 2 squared, or 4. All right, get my little calculator out. And if I've got negative 13.4 electron volts divided by 2 squared, 4, I get minus 3.4 electron volts. Okay. What's the ground state of hydrogen? Okay, or the ground state of hydrogen at N sub 1 is minus 13.6 electron volts. So what is the energy when N equal 3? Well, there again, we're looking for E sub n, and that's equal to minus 13.6 electron volts, okay, divided by 3 squared, because we're looking at 3, energy level 3, or N sub 3. So if I've got minus 13.4, I divide it by 3 squared, or 9, I get minus 1.5 electron volts, okay? So the ground state of hydrogen at N sub 1 is minus 13.6 electron volts. What's the energy when N equal 4? Well, again, E sub n is equal to E sub 1 minus 13.6 electron volts. And then I divide by 4 squared, right, or 16. I'll do that real quick. Minus 13.4 divided by 4 squared, or 16. I get minus 0.85 electron volts. All right, here we go. The ground state of hydrogen is, again, minus 13.6 electron volts. So let's find the energy at that level. So minus 13.6 electron volts over 100 squared. So we're looking at the 100th energy level. So if I put that into my calculator, divided by, 100 squared, that's 10,000. I get, minus 0.00136. So if I look at it, I get 0 electron volts. So there's no energy there. Okay? So that's where we get. We're almost at infinity there. So let's look at this. So this is a chart of the lowest 6 energy levels for hydrogen. And its ionization energy when N equals infinity. the energy more or less equals zero, and the electron will then escape the orbit of the atom. Now, all of our energies are negative, all right? And as we get the energies for the higher values, they're so close you can't really draw them together. So we stopped at n equals 6. So let's see what we can see the relationship between E, or the energy, the electronic energy, and the energy level. Okay. Well, if I look at my energy level at n sub 1, that means we're at the ground state, at the lowest energy level. N sub 2, we're at, well, we're at a little higher energy, minus 3.4. All right. N sub 3, that equals N sub 3, or the third energy level, or minus 1.51. At N sub 4, that's our fourth line, at minus 0.85. So on, so forth, and so on. So what is that telling us? So when the electron dropped to the lower energy level, what happens to the energy that's released? So remember, energy is neither created nor destroyed, it's just changed. So when that energy is released, okay, the law of conservation of energy says we've got to account for it. You can talk about it. So if I've got an electron that's on the second level, it doesn't want to be there. So it's going to drop to the lowest energy level, right? And when it drops, energy is released. Okay, let's see what happens. Let's pause. So let's see what happens. When my electron is at N2, or the second energy level, all right, it's going to go from minus 3.4 to minus 13.6. So let's see how much energy is released. If I have minus 3.4 minus 13.6, I get 10.2 electron volts. All right, 10.2 electron volts. There we go. So we got the screen up. So if I go from N2 at minus 3.4 volts, electron volts, down to N1, the ground state, I get 10.2 electron volts released as energy. Okay. So I've got 10.2 electron volts. So that energy has dropped in the atom 10.2 electron volts. So that amount of energy needs to be emitted so that the total energy of the system stays constant. And what is it emitted as? It's emitted as light. And that light, that electromagnetic wave, has light and has a color. So what does it look like? So guys, we'll find out tomorrow when we continue to explore the Bohr model. So guys, y'all have a good evening. This is Coach Scott saying farewell.